Hi, welcome to Chapter 11, Part 1, where we'll be going over series tests, finding error, and a practice problem. So, don't forget to like and subscribe.
Here we have a series. Now we have to figure out if it converges. The easiest way to do this is by using the divergence test. Now remember, this only tests for divergence. So, we find as the limit of n approaches infinity of our sequence, which is infinity. Therefore, the series is divergent.
Yay!
Here is another series. We should simplify this. When simplified, the equation goes to 30 times 3 over 4 to the nth power. Now, what does this look like? A geometric series. We can solve this using the geometric series test. The absolute value of r, which is 3/4, is less than 1, so the series converges. With geometric series, you can find the actual sum using the equation of the first term divided by 1 minus the ratio of r, or r. This gives us a final answer of 170, which is what this series converges to.
Nice.
Here we are given yet another series. We should use the integral test for this one. Now remember, there are 3 specific conditions you have to use. 1. The sequence is positive in the interval. 2. The sequence decreases in the interval. And 3. The limit of the sequence goes to 0. Nice. The conditions apply.
Now let's actually solve the integral. As we see here, we can solve this using simple u sub. Let's see where this gets us. Why is that man staring at me? Oh no, the integral goes to infinity, which means the integral is divergent. Therefore, the series is divergent as well. Note the bounds and the final answer.
Another series, it's a constant over a polynomial. We should use the telescoping series method. Lucky for us, we can quickly rewrite this into 2 fractions using partial fraction decomposition.
Nice.
But what do we do with this?
Well, we can write everything out. What will that give us? Well, we have a list of fractions. What do we do with this? Oh, we can cancel things out using the telescoping series method. So our final answer becomes 3/4. Nice, so it's convergent. We are given another series. What do we do with this one? Well, we can use p-series, which is objectively the easiest method. We can rewrite the series, and then we're given p, which is less than 1. Therefore, the series is divergent. This series we're given looks very complicated. An easy way to solve complicated things is to turn them simpler. This series looks a lot like 2 over n, which diverges. Maybe that means this series will diverge as well. Here, we are proving that 2 over n is less than our given series using different equations and inequalities. Using direct comparison, because 2 over n diverges, so does our original series.
This problem doesn't look like it can easily be solved using direct comparison. The series is positive on the interval. Another similar series is given, which is positive and diverges by p-series, so we should use the limit comparison test. The limit as n approaches infinity of a sub n over b sub n simplifies to 1, which is greater than 0. Therefore, the series diverges.
This series looks slightly different. What could it be? It's an alternating series. That means we can take out b sub n. Let's check the conditions. The limit as n approaches 0 of b sub n equals 0. And by deriving, we find that b sub n decreases on the interval. Therefore, by the alternating series test, the alternating series converges. But wait. Remember, we have to check for absolute or conditional convergence with alternating series. Here, we are using a previously used test to find if a sub n is convergent or divergent on its own. Now, what test is this? It's limit comparison. We find that a sub n is also divergent. Therefore, the series is conditionally convergent. Here we have a series that's slightly different from the others. The factorial is a dead giveaway that we should use the ratio test. We find the limit as n approaches 0 of the series. Then we simplify the terms so it's easier for us to solve. And that equals 0, which is greater than 1. Therefore, the series is divergent by the ratio test. Here we have another series where there's a dead giveaway. We should be using the root test because the series is read to the power of n. When we simplify, we get 1/3, which is less than 1. Therefore, the series is convergent. Here we have an error problem where we approximate at s sub 3. Well, this is not an alternating series, therefore we should just use regular integration to find the error, to get that the error is less than or equal to pi over 2 minus tan inverse of 3. Here we have an alternating series. We have to find when the error is less than 0.01. Because this is an alternating series, we need to find a sub n plus 1. Solving through, we get that n equals 200 at least for the error to be less than 0.01. Here is a practice problem. You are given the following problem. Pause the video right now so you can solve it on your own. The easiest method to solve this series is to list out all the series tests we can use and eliminate the ones that we shouldn't use or the ones that wouldn't apply. The divergence test doesn't work because the limit as n approaches infinity equals 0. Now let's try the direct comparison test. We can compare it to 4 over e to the n. We find that both are positive on the interval. Next, we find that b sub n, which is 4 over e to the n, is convergent by geoseries tests. Therefore, a sub n must also be convergent. Yay! Here are some pro tips. First, always state what test you are using. Second, with geoseries and telescoping, you can find the exact sum of the series. Third, with alternating series, remember to state whether it's absolute or conditional convergence. The following are some basic notes.